Good afternoon, everyone. So today we will be looking at the experiment number 10, and experiment number 10 is on the vibrations of a loaded cantilever. This particular experiment, it is able to determine the Young's modulus of wood by using the vibrations of a loaded cantilever. So in this case, we will model our system to be the ruler, which is of a wooden material, and at the end of the ruler we will attach a set of meshes. Okay, these are just simple standard meshes, the laboratory meshes of 100 gram each piece, and we are attaching this amount of mesh on this particular end, and we will need to produce a simple harmonic motion based on this particular experiment. So the apparatus that we need for this particular experiment are your ruler, meter rule, which is where you will be putting the meshes. You will also require a G-clamp to clamp the meter rule on the workbench. Next thing is we require is a stopwatch, since we'll be trying to determine the time interval taken for 30 oscillation for each of the simple harmonic motion that we consider. And we will also require the measuring devices, and the two measuring devices that we'll be using is your vernier caliper and your micrometer. So the vernier caliper and micrometer will be used to determine the dimensions of the meter rule that we have in our setup here. So the meter rule will basically need to measure the width of the meter rule. Okay, the width of the meter rule given as this distance here, and we can use the vernier caliper in that case. So vernier caliper, okay, for example, you can open up the vernier caliper and then position the outer jaws to be able to measure the value of your the width of the ruler. And likewise, you can also use a micrometer. So a micrometer can be used to determine the thickness of the ruler that we have. Okay, so we can open up the micrometer as such and twist it in place so that it does not go any further. Right, so that is how we'll be able to determine the thickness of the meter rule. So these are determined to be two values in your results if you look at your results table. Okay, so part one is where we will need to determine some dimensions of the meter rule. So for example, we'll need the width of the meter rule, okay, which is given as B. We'll need the thickness of the ruler, which is D, and we'll also need to keep a fixed length of the ruler. Okay, this is particularly for the first experiment, first part of the experiment that we will be considering, and that will be using the data table 1. So in the first part of the experiment, what we'll be doing is we will keep a 1 kg mesh. We will start off with a 1 kg mesh. So we have a 1 kg mesh right on the end of this particular meter rule. Okay, so there would be it should be evenly spaced on top of the ruler and on the bottom side of the ruler as well. So we have 1 kg of mesh that is placed on the meter rule, and we have to determine the time taken for the simple harmonic motion to occur for 30 oscillations. Okay, so we have got 3 trials, T1, T2 and T3, whereby we will need to measure the time for 30 oscillations, and then using this you can find out what would be the average time for each of these trials. And then finally you can find the period meaning the time for 1 oscillation. Remember, this is the time for 30 oscillation. You will get the average time for 30 oscillation, and then you can find the time for 1 oscillation. This will be meaning that you'll just need to divide this mean time divided by 30. Okay, and likewise, and the last column, is t squared. So basically the value that you get here, the period t, will need to be squared, and then you can find the value there. Right, so what we'll be doing is we will be reducing the mesh as we go along. So basically you start off with 1 kg, then you will remove the mesh, let's say from one of the ends as such. So you just need to unscrew the nut that is holding or that is supporting the system of meshes that are over here, and basically you will need to take a value of the time for 30 oscillations. Okay. So when we what do we mean by the simple harmonic motion? Okay, I'll just quickly show you a demonstration of how we can find out or how we can produce a simple harmonic motion using this system of meshes placed on this ruler. So what we'll need to do, just simply give it a gentle tap, okay, and after a while, basically once you simply gently tap the mesh, it will begin to oscillate, and at that same instance you start recording the time, okay, the time taken for 30 oscillations. So basically you start recording using your stopwatch the time taken for 30 oscillations. So once 30 oscillations has elapsed, you can stop the stopwatch, okay, and then you can simply record the time that is needed over here in your data table. So this is your first part of your experiment. Okay, I'll give you an idea of the results of the sample results that we have got. Okay, I'll also post this up on Moodle. So we have got the meshes that are decreasing, and we have got the time that is noted for 30 oscillations. They are also decreasing as such. And using this data table, you'll do some analysis, and then you'll plot a graph of t squared versus m. Okay, t squared against m. So I have noted that students tend to make this mistake quite often. You have t squared against m, that means t squared is supposed to be on the y-axis and the value of m should be on the x-axis. Okay, and then you need to find the slope. So using the slope, we will then look at the procedure in part 1. Okay, that is on the variation of t versus m. We'll need to use this particular equation. Using the slope, you can find what would be the Young's modulus for forward using based on this equation here. Okay, so in this equation we need the value of L, we'll need the value of B, we'll need the value of D, as well as the slope. Okay, so these parameters have already been recorded over here. For example, B, D, L, and the value of the slope given once you have found once you've drawn the particular graph. Okay, so that is part 1 of your experiment. Part 2 is quite similar in nature. The only thing changing is that in this second part we have the variation of t with L. Okay, so what we'll do is now we will fix the mesh. Okay, for example, in the first part, in table 1, you can see that the mesh are changing. We have the mesh being reduced. But in the second part, we have the mesh as a fixed value. So the fixed value is around 800 grams or 0.8 kg. And in this case, we will vary the length which the length of the meter rule that protrudes from the clamp. Okay, so we will start off by recording the value of length. Let's say we can start off with 0.9 meters. So basically this setup protrudes 0.9 centimeters from the clamp all the way to the hanging mesh. Okay, and again you will need to take the time for 30 oscillations. That means you have 3 time charts, T1, T2, and T3, and then you'll need to determine the mean T, the average T, the period for one oscillation, time period for one oscillation, and your t squared value. So as you decrease the value of L, you will see that the time interval should also eventually decrease as well. Okay, so I'll also put this up online on Moodle for you to actually have a look at the data, do the analysis, and then finally plot a graph of t squared against L cubed. Okay, so once you have plotted the graph, we need to find the slope, and then using the slope, we will then use the equation given in part 2, okay, given by this equation here. So this will be able to determine the Young's modulus for wood again. So take note, you have to determine the Young's modulus twice. We have to determine the Young's modulus in part 1, okay, using the procedure there, and in part 2 as well, okay, given in this particular form of the procedure. And then finally, you will need to determine the average value of the Young's modulus of wood from part 1 and part 2, and then compare it with the expected value for the Young's modulus of wood. Okay. There are a few questions that we need to also do as part of your discussion as well. So there are a few questions here, okay, for example, some of the analysis to be done, and then finally some questions for you to answer as part of your complete lab report. Okay, so with that in mind, I hope you have got a clear idea of how we are able to perform this particular experiment on the vibrations of a loaded cantilever, and using this we are able to determine the elasticity, the modulus of elasticity, which is the Young's modulus for wood. Okay. So thank you, and that is all.